In the last class we were learning how to express any given system in the language of bond graphs, and we learned that the essential interaction of the power as well as the information variables are represented by means of bonds between elements. So that if you have a simple circuit something like this, you have a say voltage source, you have a inductor, a capacitor, and say in addition to that there is suppose a current source here. So, this is a voltage source E, this is a current source I, C and L. Now, in that case we would write the bond graph by first observing from one end, say we start from the element E, which is a source of effort. So, we will write S E, and then this is in series with the inductor, which means they share the same flow with the rest of the circuit. So, we will say it is a one junction connected to an I element connected to the rest of the circuit. Now, what is the rest of the circuit? They share the same effort with this. So, it is a 0 junction connected to the C and to the S source of flow. So, that will be the bond graph of this. And then we say that each of these bonds have to be numbered. So, we will put some kind of a number 1, 2, 3, 4, 5. Okay. Then what is the step? You have to give power direction. Now, the power direction, from we assume that power goes out of the sources and these are denoted by half arrows. So, we are first giving these power directions. Then we assume that even though these things are not ultimate consumers of power, they take power for some time and they give out power for some time, but we assume the incoming power direction as positive. So, when power goes into the storage elements, we assume that is positive. So far so good, no problem. But we notice that there is a bond that connects two junctions, and there is no rule for assigning the power direction. So, what is the meaning of that? So, you can easily see that we can give the power direction this way as well as this way. Okay, let us figure out what will be the implication of that. Okay, the implication will have to be sort out this way, that here we have got the SE element which is giving out power. Here is the plus terminal, here is the minus terminal of that, and so when it gives out power, what is the direction of the current? It has to be that, right. So, this will be the positive direction of current. So, this power direction immediately said that this would be the positive direction of the current. Now, here is an inductor. This inductor is the power is positive when it goes into the inductor. So, power is positive when it goes into the inductor means what? What will be the polarity of the voltage across the inductor? It will be plus and minus, right. Then it will consume power. So, current going this way and this is plus and minus means that it is consuming power. Good. Now, come to this particular position. Here bond 3 which is between this. Now, this says that the power goes into the capacitance source of flow combined here. In order for the power to go into the capacitance and source of flow combined, the current is flowing this way. What will be the polarity of the voltage? Positive voltage? Yes, plus minus. Right. So, in that case this power direction implies that when this terminal is positive and this terminal is negative, that will be the positive direction of the voltage. Fine, no problem. And accordingly the capacitor voltages are defined, no problem. The capacitor consumes power, right, because the power is positive when it goes into the capacitor, and so the direction of current, positive current, will be like that. Fine. Now, this fellow is a source of flow, a current source, and it is generating power. Can you see that? The power direction is positive when it goes out of the source of flow, which means that what is the positive direction of this current in that case? As shown, as here. So, if the current actually flows in that direction and the polarity of the voltage is like this, then it pushes power into the rest of the system. Okay. So, this configuration means that this will be the positive direction of the current through the capacitor, this will be the positive direction of the polarity, and this will be the positive direction of the current through this thing. Let us now draw the same one with a opposite here we will put the opposite direction, and this 0 C. Now, what does it mean? Again, let me draw the circuit. Circuit was like this. Now, here again let us start with assuming that this is positive and this is negative. So, let us start by assuming that this sense of voltage is called the positive voltage direction. In that case, this remains the same, it giving out power. So, the current direction positive is this one is consuming power, therefore, the voltage, positive voltage direction across the inductor is this. But now, this whole combine is consuming power, right. Consuming power means it is not actually consuming power. Again, understand the essential meaning. It will be called positive when the power goes in this direction. That means, from this combine to this combine, which means that now what will be the polarity of this? Current is going in this direction, and this whole thing has to generate power and push into this, then it will be minus and plus, right. Then only if it is minus and this is plus, then only whatever is this combine will be generating power and giving to this, right. Now, if this is true, then here is a source of flow, a current source. What will be the positive direction of that current? Notice that it generates power. The power is positive when it is coming out of the source of flow. So, when will it be? When it is right. So, what was the implication? Implication of this bond was that we always started from by assuming something as positive. We started by assuming the E with a positive polarity here and negative polarity here. The rest, because of this specific power directions, automatically their positivity and negativity becomes defined. So, here this becomes positive, this becomes negative, this is positive, this is negative, and as a consequence this direction of the current becomes the positive direction of the current. While if you put it like this, then this direction of current becomes the positive direction of current. Fine. Physically what? Physically you will see that all these elements, say the voltage across the capacitor, after all you will write down the differential equations, you will solve the differential equations. After that you will see that there is some fluctuation in the voltage across the capacitor, say the fluctuation is something like this. If you had done it like this, then you would say that this is my positive. If you had done it like this, then you will say that this is my positive, that is all. So, it implies that while you are doing this, let us not bother too much about these power directions. because in the bond junction to junction power bonds, they could be anyway and just arbitrarily give it. It do not really matter, but when you want to interpret what does it mean, ultimately I am getting this waveform, what does it mean, which one is positive, which one is negative, then you have to worry about that. So, the worrying about power direction actually comes because power direction essentially talks about not the actual direction of flow, but it talks about the assumed direction of positivity. Therefore, it comes, its implication comes only when you want to interpret the waveforms. So, at the time of deriving the waveforms or deriving the differential equations, they will not really matter, and that is why even in computers these are automated. There are programs in which you simply ask the computer to give power directions, it will give. I will illustrate that. Fine. So, you have understood how to give the power direction. By the way, notice one thing. I can draw a system something like this, a mass being applied on by a force. Say there is a spring, and say at this point there is a cam. Can you draw the bond graph? Draw. Here there is a mass I element which is sharing the same flow with the force. So, it is SF I one junction to an I to the rest of the system, and this part and that part are sharing the same effort, they are sharing the same effort, right. Efforts are the same at the two ends, forces, which means it will be 0 junction connected to a capacitor C element spring, and 2 this is a cam is source of flow. Notice that you have arrived at exactly the same bond graph, which means that circuit and this mechanical system are physically identical. Force is a source of effort. Oh, sorry. Yeah. Source of effort. So, here also you will give the power directions like this, and then this one could have this direction or that power direction. What does it mean? It will mean physically exactly in the same sense that the two directions of the current, this was positive in case of this direction and this was positive in case of this direction. We saw that. Here its implication equivalently will be that you will find that this motion in one case will be positive and this direction of motion in another case will be positive. That is it. Okay. You can just work it out how it comes, because if you put it like this, it means that the power essentially goes from here to here, and accordingly if say this direction is your positive direction of say x, then F causes a positive power flow. So, in that case it goes into this particular direction will become the direction of positive flow if the power direction is like that. So, that is all, there is no further difference between the two. Okay. Now, so far we have been handling the one port elements. We have been handling elements like I with one port, C with one port, R with one port, SE with one port, and so on and so forth. Why do they have one port? Because only with one bond you can define the effort and the flow variable. One bond carries its effort and the flow. So, if the effort information is flowing this way, the flow information is going that way. So, one bond suffices. But there are some elements in which one bond does not suffice. Imagine that there is a transformer with some kind of a magnetic link between them. What will happen? You apply a voltage, you see another voltage appearing here with some transformation ratio, turns ratio. If you apply a current here, a current will flow here again with a turns ratio, which means there will be an effort and flow in this side, and there will be a effort and a flow in this side correspondingly, and they are related by they are actually drawn in terms of this being whole thing being represented by just one element T, a transformer TF, with two bonds in the two sides, because without that you cannot completely represent it, two bonds in the two sides. So, here is a E1 F1 and here is a E2 F2, and they are related by what? Okay, the convention, see, the voltage here is a turns ratio times the voltage here, a flow here is a turns ratio times the flow here, but then that transformation ratio is represented by this say mu, this is represented with an arrow like this. Why? The convention is that you could express the effort here as a function of the effort here, you could also express the flow here as a function of the flow here, but the convention is to go by the flows. So, it says that F2 is mu F1, that is it. F2 is equal to mu F1. Now, the power that comes this side should be equal to the power that goes into this side. So, E1 F1 is equal to E2 F2, which immediately implies that E2 is equal to 1 by mu E1. So, this is the relationship that is depicted by this symbol. The symbol is, notice that it carries a arrow, because if you give the arrow in the opposite direction, then it would mean F1 is equal to mu F2. In that sense, it has to have an arrow. So, which one is in the left, which one is in the right does not matter. What really matters is the direction of the arrow and mu is a transformation ratio. Clear? What can be a mechanical transformer? Gearbox, yes, gear is a mechanical transformer. Not only gear, levers are mechanical transformers. Imagine that you have got something here connected to a lever to something here, so that is also let it be connected by means of say spring damper arrangement to say ground. This with a ratio A by B, that is also a lever. Why? Because the flow here is related to the flow here by means of what relation? No, minus B by A, because if it goes up, it goes down. So, this motion here, so F2 is minus B by A times F1. So, this minus B by A becomes the mu. Fine. So, that is also to be represented by means of a transformer. In that case, you would write it something like this: transformer with a transformation ratio minus B. Fine. And of course, gearbox is where you can directly see the flow here is giving rise to a different flow in the other side, and accordingly the efforts are also divided. So, these are the transformer elements. So, again what is the transformer element doing? It is converting a flow into a flow, an effort into an effort. Is it possible for an effort to be converted into a flow and flow into an effort? Yes, it is possible, and that element is called a gyrator. Which is represented as with some mu as the transformation ratio, but in this case I will show that there is no need to put an arrow. Suppose it is E1 F1 and E2 F2. In that case, the relationship would be E2 is equal to mu F1, not E1. So, the flow here multiplied with the multiplying factor m mu gives you the effort here. And how is F2 given by E1? Let us see. Since this is also not a power producing element, so you can write E1 F1 is equal to E2 F2. So, this and that combined implies what? E2 is equal to mu F1 and E1 is equal to mu F2, which means that there is no meaning in putting an arrow. Both sides is the same thing. Effort here is mu times F2, effort here is mu times F1. Okay. Likewise, flow here is 1 by mu times E1, flow here is 1 by mu times E2. The question, next question, natural question, where is such thing to be found? Let me give an example. Suppose you have a DC machine. In a DC machine, you have applied something and something results. And what is the relationship between them? Relationship between them is a DC machine. In a DC machine, what is the relationship between the torque produced? Torque is K phi armature current IA. Torque is the effort in the mechanical domain and IA is the flow in the electrical domain. So, this is the multiplying factor and this whole thing is converting and a flow into an effort, right. So, you would have to write this, represent this as a gyrator with multiplying factor K phi. So, here it is E1 F1 and here it is E2 F2. This bond is numbered 1, this bond is numbered 2. In that case, notice that here is the mechanical side say and here is the electrical side say. We have already shown that E2, which is T, is K phi times F1, which is IA. But what about this relation? Let us see. E1, what is the effort in the electrical side? The back EMF, yes. So, EB is K phi into the number of speed of rotation n in RPS. So, you have n as what? The flow in the mechanical side. So, exactly this relationship is holding, right. E1, which is the EB, is K phi into the speed of rotation, which is the flow in the mechanical side. So, the DC machine, at least the ideal DC machine, is nothing but a gyrator. In fact, all machines are. you can easily see that in all machines the current signal is converted into a torque signal in all electrical machines or actuators. The current signal is simply, if you assume that there is a magnet, it is calling another is pulling a piece of iron, then the magnetic force is dependent on the current, and the force is being produced in the mechanical domain. So, that is a effort. So, wherever you have such things, it is essentially gyratory action. So, we understand these things now. Now comes a very interesting concept. We have said that in the bond graph, we are representing the structure of the system completely. So far, we have been worrying about the direction, the elements, representation of the elements, and how power flows. But then power is composed of two things, the effort and the flow, and we have already made the statement that no single element can decide both. So, these are information variables, the effort and the flow, both are flowing, but no single element can control both. So, as we draw the complete structure, in that complete structure the information must be flowing in a very specific way. How is it flowing? Who is deciding that? That is what we will concentrate on now, and that issue is called the causality. To illustrate, say you have got a voltage source connected with a resistance. Who dictates what? The voltage source, the SE element, here the bond graph will be simply SE connected to one junction connected to R, and the power direction will be like this, of course. But then who decides what? Notice the SE element decides the effort, but it cannot decide the flow. So, the effort information flows this way, and the flow information, the resistance dictates the flow, that flow information goes this way. So, there is a direction of flow of information through the whole structure of the system. Everybody is deciding something, and an interesting thing is to keep track of who is deciding what. For example, in this simple thing, the SE element is telling the rest of the system, okay, in my bond the effort is this, but he is not being able to decide the flow. The rest of the system will decide the flow, while the resistance in this particular case is deciding the flow. Now, that, okay, take the opposite case. Suppose this fellow is a current source, then it is SF connected to one junction connected to R, again power direction like this. Who is deciding what? The source of flow, the SF element, the current, that is deciding the flow, but it cannot decide the effort. Who is deciding the effort? The resistance. So, the resistance is deciding the effort. So, the flow direction, flow information is going this way, and the effort information is going that way. Now, these are marked by something called causality. But before we start marking it, let us try to understand why is it causality. Let us try to understand who decides what again, but in the relationship to the capacity of inductive elements. Say, take a inertial element. Take an inertial element. Now, in the inertial element I, we have got a bond, right. Now, in that bond, suppose it is E and this is F, there is a specific relationship between the two. What is the relationship between the two? What is the relationship between the two? The flow is equal to something, a constant or a function, times integral of minus infinity to present effort, right. So, here it is constant or function. Now, notice the relationship between these two. In order for the flow information to be generated, it requires the whole history of the effort information, right. So, what causes what? If I ask you what causes what, obviously effort causes the flow, because the effort information is prior, it has already happened, and that is why the flow happened. Can you see? The flow now is determined by the history of the effort, and in any causal system, causality means that something causes something, the what causes should be preceding what is the effect. So, cause precedes the effect, and that is why we say that there is a causality, means I have done something, due to that something else is happening. So, that is a history, and that effect is what happens. So, out of the flow and the effort, what is cause, what is effect? Effort is the cause and flow is the effect. So, that is a very important. So, this is the cause and this is the effect. So, whenever there is an inertial element, that is the very important concept, that in order for a flow to happen, there has to be history of effort, and in order to calculate the flow, you will need the history of the effort. So, it is not only concept, it is also needed for your calculation. You will ultimately write a differential equation that has to take this fact into account. So, if you say that here is a I element along with it a bond, then what is the direction of flow of these informations? This says that the flow information, the effort information must be going this way, and then the flow information comes this way. Clear? In these cases, we could say that the SE element gives out the effort information, receive the flow information. This resistance receive the effort information and gives out the flow information. Here similarly, this fellow gives out the flow, receives the effort, this fellow gives out the effort, receives the flow, fine. But in this case, in this bond, it is very hard way understood that this fellow must be receiving the information about the effort in order to give the information about the flow. So, the effort information must be flowing this way. So, I will put an arrow direction, this is the effort information direction and this is the flow information direction. All right. Similarly, in case of the compliance element, in case of the compliance element, C connected with the bond with a effort and a flow. What is the relationship between them? The relationship is effort is equal to a constant or a function times integral minus infinity to present flow dt. So, the capacitive element must receive the information about the flow in order to generate the information about the effort. See, we do not notice this all the time. Say a capacitive element is like this, it must be receiving a flow in order for it to generate a voltage difference. So, the voltage difference is the effect, the cause is the flow, cause is the current. Okay. So, in this case this particular element has that causal structure in it, without that it cannot function. So, here the directions would be effort information is given out by this fellow, but the flow information has to be received by this fellow. Clear? Now, therefore, we understand that whenever we draw a bond graph, in the whole bond graph each bond has a specific direction of flow of the informations. If effort goes this way, flow goes that way, and each of the elements has specific preference in choosing one of them. Compliance element will naturally receive the flow information, give out the effort information. A inertial element will receive the effort information, give out the flow information, so on and so forth. Now, this is normally denoted by a specific convention. Who determines what? Who causes what? That is normally given by means of a specific convention. The convention is, imagine you are holding a syringe in your hand, like this. Can you show? Yes, a syringe in your hand. So, if you press it, it will go that way. So, imagine that is the flow, then you are holding the base of the syringe and you are pushing it. The convention is to give a stroke at that end. So, here flow is that way. So, I will give a stroke like this, means that we are, imagine that we are holding a syringe and pushing it, then the flow will go in that direction. The moment you see a stroke here, it is called the causal stroke. You would know that the effort is coming this way and the flow is going that way. So, that is the convention for the inertial element. Similarly, for the compliant element, what will be the point at which you put the stroke? Here, because the flow is going that way, right. How do you put the stroke in case of the AC element? AC element determines the effort, but has to receive the flow. So, flow goes this way, like this. SF element here, right. What about the R element? Well, the R element is something that can take both, and depending on the way it is connected in a circuit, it either determines the flow information or determines the effort information. It cannot determine both, but in this particular case, the way it is connected, it is doing what? No, it is receiving the effort information, giving out the flow information. The flow information is going that way, so it is like this. In case of this, it is receiving the flow information and flow information going this way, and it is giving out the effort information. So, flow information is going in this direction, so it will be like this, like this. Okay. So far so good. Let us now talk in terms of the transformer element and the gyrator element. Transformer. Here is the E1 and here is the F1 and here is the E2, F2. How will you first give the power direction? If power direction is positive this way, it has to be positive that way. So, power direction is rather simple. Now, in this case, if the flow information is coming this direction, since F2 is equal to mu times F1, the flow information is going in that direction. Of course, the opposite could also be true. If the flow information comes this way, it will be in the opposite direction. So, it will either be this stroke or that stroke. Both are possible. Either it goes this way into the other side, or the flow information is coming this way and goes through the transformer. And goes through the transformer. What about the gyrator? Here also the power directions would be in the same direction, because power goes through. There are two possibilities again. So, let me draw two. Now, here say here is E1, here is F1, here is E2, here is F2. What is the relation? The relation is, we have already written that, relation E2 is equal to mu F1. So, if this bond F1 is bringing in the flow information, goes out as the effort information. Is that clear? So, if this bond brings in the flow information as this, if you put the stroke here, means the flow information is going this way. In that case, E2 is mu times F1, and so what goes out is the effort information. If this fellow takes out the effort information, it must be bringing in the flow information. So, the stroke has to be here. In a similar vein, in case of the situation where this bond is bringing in, or say this bond is bringing in the effort information, not the flow. So, here is E1, F1, and here the E1 is bringing in the information. In that case, flow information is going that way, and then the flow here F2 is then determined by the gyrator element times the E1, and so the effort information has come in, the flow information must go out, and so the stroke has to be here. Okay. Now, once we have understood this, the complete information necessary to draw the bond graph is ready, and in the next class itself we can start deriving differential equations. Only this much was necessary. The main advantage is that once a physical description of the system is converted into its equivalent bond graph structure, the complete information necessary to write the bond graph is there, and then not only that, the derivation of the differential equation will be very algorithmic. You have to blindly follow a certain procedure in order to obtain the differential equations. It is so algorithmic that passing an exam is very simple. It becomes very simple because you have to almost blindly do it. Some people may like it, some people may not like it, but the major likable aspect is that you do not even have to derive the differential equation. It can be done by any damn fellow, and the dammest fellow is the computer. So, we generally give the job to a computer to do it. So, normally, yes, for our practice we will practice obtaining the differential equation, because you have to have the feel for it. But in actual practice, when you have the task of writing the differential equation for a very big system, obviously, if you want to do it by hand, it will take you ages. So, all we do is to just figure out the bond graph, give it to the computer, it may derive something like 55 dimensional differential equation, no problem. But if the same thing has to be done by you, you know that it is going to be a nightmare. So, that is the main advantage of the bond graph methodology. Okay. So, let us now figure out a few simple bond graph structures. and how to give the bonds. Let us start with this simple system. We have already done the rest. How will you give the causal directions? Let us do that, and there will make a very strong point, that is, say the AC element. AC element gives out the effort information and receives the flow information. So, the causal stroke will be here. The SF element, it gives out the flow information and receives the effort information. So, the causal stroke will be here. Fine. Now, notice an important thing, I will come back to that. Suppose there is a one junction connected to 4 bonds, and suppose one is bringing in the flow information. One junction is a flow equalizing junction. It is a series kind of electrical circuit. It equalizes the flow, and immediately you would notice that it will equalize the flow. That means the flow information, if it comes through one bond, it must go out through the other 3. Okay. It cannot be that a one junction is receiving the flow information from 2 directions. It cannot happen. Forbidden. Always, if there is a one junction, only one bond must bring in the flow information. So, let me write it. Similarly, if there is a 0 junction connected to 4 bonds, then the flow information can be brought in by any number, but the effort information, if 0 junction receives the effort information, then it must distribute that information in the rest of the bonds. It can't help it, because it is a effort equalizing junction. So, if one bond brings in the effort information, it is flow this way, effort this way, immediately the causal structure of the rest of the bonds would be determined. So, it will be this. This means that the effort information is coming in by means of this bond and getting distributed by means of the other bonds. Is that clear? So, these are, so in a 0 junction, only one bond, fine. Good. On that basis, let us attack this problem. Here we have got a SF element, here we have got a AC element, and here there is a I element. SE element has brought in the effort information. The one junction can still accommodate more. So, there has to be a source from which the flow information comes, and it is easy to see that here is a I element, inertial element, which gives out the flow information and receives the effort information. The moment this one junction has received the flow information, it must give out the flow information in these 2 directions. Immediately this direction becomes determined. Okay. Now, this 0 junction has received flow. There has to be something that determines its effort. Obviously, the C is that element which receives the flow information and gives out the effort information. So, the moment you give it, it is fine. Notice the logic that we followed. Here, if a one junction receives the flow information, then its causal structure is completely determined, you can't help it. A zero junction receiving the effort information, its causal structure is completely determined, you cannot help it. That is why this one and this one will be called the strong bonds, and the others are weak bonds, in the sense that this fellow in a strong way brings in the flow information, this fellow in a strong way brings in the effort information. Here in this case, can you identify the strong bonds? Is this a strong bond? No. Is this a strong bond? No. But this and that 2 and 4 are the strong bonds. All right. Let us do another circuit. Okay, we have done a problem in the last class where we had no, let us not do the circuit we have done enough. We have applied a force on a mass, there is a spring damper arrangement connected to say a cam. How did we make the bond graph in this case? We said that the one junction is connected to the SE element here, connected to I element here, and that is connected in the two directions to two zero junctions. Here it was a C element, here it was a R element. We have already done that, that is why I am not repeating the whole logical structure. In that case, in order to complete this bond graph, what we will have to do? We will have to first put the power directions, and power directions can be put started from the sources like this, then the individual elements like this. Now, these can be power directed anyway. So, let us just put just any power direction, no problem. These only say what will be the positive direction of the power, that is all. Now, give us the causalities. The causality, when we start assigning it, we start again from the sources. Here is the source of flow, it gives the flow, so it will be causal this way. Here is the source of effort, which gives the effort and receives the flow, so it will be causal this way. So, this one has become a strong bond. Can you see that? Naturally, it immediately tells that these two must take away the flow information. It gets determined. But then nothing else is now determined, because here the flow information has come, but this is zero junction. This here a effort information has come, but it is a one junction. So, let us go to the storage elements next. Here is the I element that naturally receives the effort information and gives out the flow information. So, it will be causal this way. So, the flow information goes this way, and it goes into a one junction, which is a flow equalizing junction. Immediately the flows in the other junctions will become determined. Fine. So, here is a zero junction in which the flow informations have come, but as yet I do not see any effort information coming in. So, the effort information must be generated by the C junction, which is its natural property. Its property is that it receives the flow information, gives out the effort information. So, its causality will be here. So, the flows added up goes into the C and the effort is given out by the C, which is equalized by the 0 junction. Done. Now, let us come to this R element, which can, as we have seen, take both the causalities, but in that case what will be the causality? Will it generate the effort information or will it generate the flow information? Effort. Yes, because of the same reason that it has already received the flow informations and the flow information is going into that, and this 0 junction must receive the effort information. So, it has to have the causal stroke like this. Then this bond graph is complete. Fine. Okay. So, with that much understanding, we will embark the next day on the art of obtaining the differential equations. Fine. Okay. Thank you very much.